A stainless steel fork rests quietly on a dining table, reflecting warm yellow light. Its surface is smooth, cool, and clean. Few would guess that to achieve this calm, polished appearance, it endured a manufacturing process more extreme than that of many heavy industrial materials. If metals had medical records, stainless steel would likely be listed under multiple trauma. Its journey begins with iron ore, nickel, and chromium-anonymous minerals extracted from deep within the earth. They are fed into an electric arc furnace, where temperatures can reach 1 Ba'icham. That number is not trivial. It exceeds the temperature of typical volcanic lava and is hot enough to melt most structural metals. At that level of heat, the original crystal structure collapses completely. Everything becomes a glowing white liquid. No shape remains. No physical memory of the original ore survives. To put 700 degrees Celsius into perspective, steel begins glowing red at around 500 degrees Celsius, turns bright orange at 900 degrees Celsius, and at 700 degrees Celsius, it shines white like a light bulb filament, but on an industrial scale. The furnace does more than melt metal. It allows elements to blend uniformly. Chromium must reach at least about 5% to create corrosion resistance. In the widely used 304 grade stainless steel, nickel typically accounts for around 8%. These percentages may seem small, yet missing even a few percent can significantly reduce corrosion resistance. Once molten, stainless steel enters another refining stage: gas purification. A mixture of argon and oxygen is injected into the liquid metal in a process called AOD, argon-oxygen decarburization. Oxygen reacts with excess carbon, forming carbon monoxide gas that escapes. Argon acts as a dilute, carefully controlling the reaction and preventing excessive chromium loss. Instead of filtering impurities through paper, engineers use high-pressure gas chemistry inside a glowing metal bath. Too much carbon makes stainless steel brittle and vulnerable to corrosion along grain boundaries. Removing carbon is not about aesthetic cleanliness. It prevents a form of internal corrosion that can occur when the material is reheated during welding. A small deviation at this stage can mean the difference between a product suitable for medical or food-grade use and one that fails industry standards. After refining, the molten metal is cast into slabs. These slabs remain massive and intensely hot, weighing several tons. From here begins the hot rolling process. Enormous rollers compress blocks tens of centimeters thick into much thinner sheets. The applied force alters the internal grain structure. Metal grains elongate in the rolling direction, increasing mechanical strength. The process does not stop with hot rolling. After cooling, the steel undergoes cold rolling to achieve even more precise thickness, sometimes reduced to just a few millimeters. 1 millimeter is roughly the thickness of a bank card. A once heavy slab becomes a thin, flexible sheet ready for cutting and forming. Cold rolling strengthens the material further through work hardening. However, this also makes it more difficult to shape. To restore balance, the steel is sent through annealing. It is reheated to a high temperature and then cooled under controlled conditions, allowing the crystal structure to reform in a stable configuration. Annealing effectively resets the internal structure after it has been strained. Even at this stage, the surface is not ready for the dining table. After rolling and heat treatment, stainless steel carries thick oxide scale and residues from high-temperature processing. The next step is pickling acid treatment, often using a mixture of nitric and hydrofluoric acids. This bath dissolves unwanted oxides and surface impurities, revealing clean metal beneath so that a thin, stable chromium oxide layer can form properly. The acid bath is not decorative. If heavy oxide scale remains, stainless steel will not achieve optimal corrosion resistance. The surface must be thoroughly cleaned so the passive chromium oxide layer can develop evenly. Afterward, the steel may undergo mechanical or electrochemical polishing to achieve its reflective finish. Only then is the sheet stamped into spoons, forks, knives, or machine components. A small fork may originate from a slab that once weighed several tons. Its journey includes melting, gas refining, pressing, stretching, reheating, and acid treatment. Each step aims to control the structure at a microscopic level. When you hold that fork, you are touching the result of dozens of hours of thermal and chemical processing. Its shine is not a coating. It is the outcome of carefully engineered structure. If a simple kitchen utensil must pass through such rigorous stages, materials used in ships, chemical plants, or medical devices face even stricter requirements. The story of stainless steel does not end at the dinner table. It opens a broader narrative about how humans manipulate matter at the atomic scale to serve everyday life. The next time you notice the reflection on a spoon, you might remember the 700 degrees Celsius furnace and the acid baths behind the scenes. And if those circles of industrial fire still seem insufficiently dramatic, there is another chapter, how stainless steel protects itself long after surviving all of them.